Okay, so let's take a look at today's lesson. Today's lesson we're going to look at particle motion again. We looked at particle motion several weeks ago, probably more over a month ago, with relation to derivatives. At that time all we knew was how to take derivatives. And we talked about particle motion in that context. So I want to remind you what we did. It doesn't mean that we're going to not ever do that again. It's just we're going to have a different way also to do it. So when we had the derivative and we wanted to find displacement, we really actually needed the position to find displacement. We couldn't have just had the derivative back then. We would need the actual function. And to find displacement, if you recall, we just did end minus beginning of the actual position function. Remember that? So if we were let's just say we were looking to find, from say t equals 0 to t equals 3, of some kind of function. Let's say we were looking to find the displacement of, the particle that was moving. We would have done s of 3 minus s of 0, right? That would have given us our displacement. Remember that? That's what we would have done. When we had to find distance, if you recall, that was much more difficult because we know that the particle can move, right or left, and then when it moves left, it has negative. It's negative, and so that would be a problem for us with distance. It would negate that part. So if you recall, we found the derivative, or we had it, and we set it equal to 0, and we did a sign chart. Let's say in this case, let's say 2. Let's say that's what our sign chart was. Between 0 and 2, it was negative, the velocity was negative, and between 2 and 3, we were positive. And so what we did then is to find the distance, we took each section. Recall, remember we did the absolute value of end minus beginning, like absolute value of s of 2 minus s of 0 plus. So absolute valuing it would negate, get rid of that negative. And we don't really have to do the absolute value of the second piece, but that's just what we did. So s of 3 minus s of 2. And that would have given us our distance, right? This gave us distance, and this gave us displacement. Okay, that's before we knew how to integrate. Are you with me? And you can still do that. That's still a viable technique. But now we know how to integrate, and we have more options available for us. We don't have to just rely on these two options. If we want to find displacement, what we can do is use this formula. Okay, so I would integrate from my beginning time to my ending time of my velocity. Integrating velocity gives me displacement. That's what it does. So let's look at this picture over here. If I want displacement, I would simply, collect or accumulate the area under the curve all the way across, going forward. If it was above the x-axis, it would be positive. If it was below the x-axis, it would have a negative sign. I would just accumulate the whole thing, right? And that would give me my displacement. Okay, so that's how to do it with integration. We would need, now this is important, we need velocity to do the integration for. Remember when we first started doing integration, I explained that aha moment I had when I'm like, how in the world can area be distance? Remember we had, if this is our rate, see our velocity is here, our rate, and this is our time. The rate and the time is that product is our distance, that area is the distance. So with displacement, we treat, above the curve, under the curve, we just treat it as it is, positive, negative, positive. If we want distance, though, it becomes a little bit more difficult, just like without the integral, right? It was more difficult with just derivatives. It's a little bit more difficult. We actually have to do the absolute value of the velocity. That's what we have to do if we want distance. So looking at this graph right here, what I would have to do is I would have to alter this piece and force it to be positive if I wanted distance. So I would have to force it to be positive to get my distance traveled. And that's what this absolute value does. It's the absolute value of velocity, not of the result. So some students want to put the absolute value on the outside of here. That really doesn't do anything except for make our displacement positive. I would need to absolute value the actual velocity function and force it to be positive all the time. Okay, so that's how we would do distance with an integral. Again, we're integrating velocity. And actually, when we integrate just regular old velocity, that's displacement. When we integrate speed, so the absolute value of velocity is speed. When we integrate speed, we get distance. So those are two really important concepts for us to kind of absorb and really think about when that happens. So this is it in words. Integration velocity over time produces displacement. Integrating speed over time produces distance traveled. Okay. So these two formulas right here, those will certainly be on formula quizzes. Those are important formulas. We need to know how to find displacement using an integral. We need to know how to find distance using an integral. So those will be on formula quizzes. Okay, these aren't going to be on formula quizzes. Really, this is just highlighting a relationship, the relationship between velocity and position. If I integrate velocity, I get position. I mean, it's just talking about the relationship. That kind of is like common sense to us right now. If we integrate velocity, we're going to get position. If we integrate acceleration, we're going to get velocity. So these are formulas that they're not going to be on a formula quiz. They're just talking about trying to highlight the relationship between those types of functions. That's all. Okay, are we okay with that? This formula you would have probably memorized in, pre-cal or algebra 2. This is on particle motion, this formula, where t equals 0 at the velocity at time t equals 0, so that's our s naught, our initial position, and v naught, our original velocity, initial velocity, would go here and here. And that number, that a, remember that was acceleration due to gravity. Remember that from back when? Acceleration due to gravity. If we're in meters, it's 9.8 meters per second. If we're in feet, it's 32 feet per second squared. And so we don't need to memorize these. I'm going to show you how we're going to use calculus to derive them. I mean, that's how they derived them, was using calculus, so we don't need to memorize them. So they're there. Just I wanted to highlight what we knew before, and I'll show you how we can create those from scratch without having to memorize that. So since we don't have to memorize these are not going to be on a formula quiz, right? You don't have to memorize them. We can create them from scratch. And I'm going to show you how on the second example on the next page, how to create those formulas from scratch. Okay? So any general questions before we start the examples? All right, let's go to the second page. So our first example is telling us we have a particle moving with a velocity in meters per second along an s-axis. Find the displacement and distance traveled by the particle. So they're giving us velocity, and they're giving us our time, the time between pi over 2 and 2 pi. So what we need to do is we're going to do displacement first because that's the easier one. So displacement is just going to be equal to the integral from pi over 2 to 2 pi of cosine t dt. I mean, we just compute that integral, we're going to have our displacement. So let's do that. So our antiderivative of cosine, so if we were taking the derivative of something and we got a positive cosine, what would we have taken the derivative of? A sine. So this is sine t evaluated from pi over 2 to 2 pi. So let's do our f of b minus f of a, our fundamental theorem. So sine of 2 pi minus sine of pi over 2. So unit circle values, yay. Right, let's do our unit circle values. Sine at 2 pi is 0 minus sine at pi over 2 is 1. So our displacement is -1 meters. We're in meters, aren't we? Yeah, meters. That's our displacement. So displacement can be negative. We talked about that before, right? It can be negative. That just means that we are, 1 meter backwards from where we started. That's all. 1 meter to the left if you're thinking of in the coordinate plane. All right, so that's displacement. All right, so now let's take a look at distance. So for distance, we need to integrate the absolute value of cosine. Well, that's not just as easy as just writing the absolute value around cosine in my integral. It's not, unless I have a calculator. If I have a calculator, it is just that easy. You would just put the absolute values around cosine and use your calculator. But when we're doing it by hand, it's not quite that easy. We can't just put absolute value around it and it's going to be absolute value. We have to investigate where is it negative and where is it positive. Right? We got to look at that. So we need to do a sign chart on cosine. We need to do a sign chart. We need to find its critical numbers, and we need to figure out where it's going to be positive and where it's going to be negative. So let's do that. So cosine t equals 0. So t would be 0. So cosine is 0 at, let's see, pi over 2. All right, cosine is 0 at pi over 2. So t is pi over 2 or 3 pi over 2. We're just worried about this interval right here. So we need a sign chart starting at pi over 2. 3 pi over 2, and then actually I'm stopping at 2 pi. It's not really a critical number, but that's the end of my domain, so let's just stop right there. I'm taking the first derivative, which is velocity, and setting it equal to 0. I'm doing a sign chart on velocity so I can determine whether we're going right or left, whether we're moving positive or negative direction. That's going to be important to me as I calculate my distance. Right, I need to know which sections are positive and which are negative so that I can alter them. Does that make sense? Okay. Now, I'm not really good with numbers in my head. You can pick numbers in between here and plug them in. I personally would rather graph it. It will be way faster for me to graph cosine than it would for me to calculate all those values. So cosine looks like this, right? Pi over 2, 3 pi over 2. So we're looking, of course, the sign chart is the y value of the function that we're doing the sign chart on. That's what it is. So the y value of cosine between pi over 2 and 3 pi over 2 is negative. That section is negative. Now you can do it by plugging in a number. That's okay. You can do it that way too. But with trig, for me, it's faster to graph it. Now, cosine is positive between 3 pi over 2 and 2 pi. Okay, so that's going to be important for me as I set up my integrals to find distance. I'm going to have to do 2 integrals. It's like when we did the absolute value graph. Remember a week or so, a couple weeks ago, when I showed you how to do the absolute value, integrate absolute value? We had to do this. We had to see where we're positive, where we're negative, and we had to split the integral into pieces. That's what's going on here. So distance is going to be, I'm going to have to do the opposite of my first integral, right? Because this is negative. So I've got to do the opposite of pi over 2 to 3 pi over 2 of cosine t dt plus this section is positive, so I don't have to make any adjustments to it at all. So the integral from 3 pi over 2 to 2 pi of cosine t dt. So that's what I need to solve in order to find distance. Okay, by hand. Alright, so let's do, we had already done the antiderivative, right? We know it's cosine. So why don't we just look at the work that we did previously. So this is going to be a negative, when we integrate cosine we get sine. So this is going to be negative sine evaluated from pi over 2 to 3 pi over 2 plus this is going to be just regular sine evaluated from 3 pi over 2 to 2 pi. Okay, so that's what we're looking at for our distance. So I basically have negative, I'm going to pull that on outside, so I would have sine of 3 pi over 2 minus sine of pi over 2. I'm doing my f of b minus f of a, right? The opposite of sine of 3 pi over 2 minus sine of pi over 2 plus sine of 2 pi minus sine of 3 pi over 2. Okay, I know I'm going kind of fast. Are we okay? Is everybody caught up? Am I moving too fast? Okay, so now let's do our unit circle values. So we know sine at 3 pi over 2 is -1, and sine at pi over 2 is 1. Okay, sine of 2 pi is 0, and sine of 3 pi over 2 is -1. Okay, so we do that arithmetic. Right, so I have a -2, a -2 is a +2, and minus a -1, so my distance is basically 3 meters. 3 meters is my distance. Okay, so that's how we would find displacement and distance by hand using an integral. Okay? All right. So let's take a look at our word problem here. This is the problem that's we're going to use. We're going to use this to build those equations from the other page. So we have a scenario where, let's see, Nolan Bryan, he can throw a baseball 150 feet per second. And we're trying to figure out if he could, if he threw it straight up and he had an upward velocity of 100 feet per second from a height of 7 feet, could he throw it this high, 208 feet high, to hit the ceiling of the Astrodome? That's our scenario. So what we're going to do is we're going to actually build this from acceleration up. So we're in feet. So what is the value for acceleration due to gravity in feet, if we're using feet? It's a -32, right? It's 32, right? But gravity is a downward force, right? It's pulling down. It pulls things down. So our acceleration A of t is going to be -32. That's our acceleration. It's gravity is a force that's going down. No, we're talking acceleration. Okay? So that's our acceleration. It's constant, right? Does the acceleration for gravity change? I mean, isn't it always pulling us? Like it's a constant. So there's no variable there. It's just a number. Now to get velocity, we need to integrate acceleration, right? That's what we do. So let's do the antiderivative of acceleration. So v of t, I do the antiderivative of -32, and I get -32t plus c. Okay, so let's find what c would be. All right, so that's velocity. They're saying it's 100. The initial velocity is 100 feet per second. Initial means t is 0, right? If I put a 0 here and 100, can we see that our c would be 100? Does that make sense? Do I need to write that out? Are we okay? So the initial time would be 0. I'll just write out 100 equals -32 times 0 plus c. So c is 100. Right, so my velocity equation is -32t plus 100. There's my velocity equation, which is great. I need velocity, but I actually need my position equation. Right? We need to know how high he's going to be able to do that. Yes? Okay, so this velocity is positive. It's going up, right? The direction is up, so it's a positive number. So I made this 0, right? I put a 0 for t. Are we okay? Yes? Okay. So now I need my position, so I've got to do the antiderivative of velocity to get my position. Right, so s of t, so the antiderivative of -32t, so I would add 1 to the 1, I get 2, divide by 2. So that's -16t squared plus 100t plus c. Okay, do we have an initial position? We do, don't we? The initial position is at 7 feet. So I zero out my time at 0, so 0, 0. C is going to be 7. So my s of t, -16t squared plus 100t plus 7. Okay, so now I have all the equations that I need. Those equations, if you had memorized the formulas on the previous page, you could have just written the equations down, but why when that would just take us like a second, right? We don't need to memorize them. You can if you want to. So we need to know if he can throw the ball 208 feet high. we really need to know a maximum, don't we? We need a maximum. So how do we find maximums in calculus? Yep, we take the derivative set equal to 0. That's what we need to do. We need to find the maximum time. If I knew the time that it was at its maximum, I could figure out the height that he was at its maximum, right? If I knew the time. So I'm going to take my derivative, which is, so 0 equals negative 32t plus 100. So I have 32t equals 100. I solve, and I get, what, 25/8. If we want to verify whether that's a max or a min, we could do a sign chart, right? With 25/8, that's our 0. And actually, it is the maximum. That would be our sign chart if we wanted to do that. So now what do I do? How do I know how high he's thrown the ball at the maximum? I just sub that into my position, right? That's what I would do. And of course, you would have a calculator for this. So, which makes it really important that you understand you have to show the calculus work. Yes, you could do this all in a calculator and give me a number answer. That is not going to get you any credit. The calculus is what gets you credit. Okay, so the calculator is just to help us with difficult numbers. It's not to like do our work. So I'm going to do S of 25/8. So I get negative 16 times 25/8 squared plus 10 times 25/8 plus 7. So I do all of that, and I get 163.25 feet. So now we have all the data that we need to answer our question. We have not answered the question. We have to actually answer the question that they ask. Could Nolan Ryan have hit the ceiling if he were capable? Could he have? And the answer is no, but no is not sufficient. You cannot ever write a yes or no answer without a reason. Okay, so yes, it is no, right, because the maximum is 163. So one way to write it would be no. We could say it's 44.75 feet short of the ceiling. That's really quick to write. There's nothing really serious there, right? But it explains our position. No, it won't work because of this. We've gathered all the data. We've done our calculus. We know what's going on. And no, that would not work. Okay? And so that is working a particle motion with just straight calculus and not using the formula. Okay?